Okay, let's start the lecture. So today we are going to move on to the next module, which is clustering. So this is because our project, programming project, is related to clustering. It's not so much, but I think it's better to move the clustering beforehand. Usually we actually deal with classification and regression first, then talk about clustering. So some of the stuff might look abrupt, but anyway, I'll try to explain. So first of all, we need to know what is this kind of clustering analysis. So one of the intuitive idea is that we try to group things together, especially if we have absolutely no idea. Okay, so if we, for example, as this picture shows, just pretend that you do not know anything, but just, I mean, it should be pretty obvious that one of the objects, right, are very different from all the others. Sometimes, I mean, this also demonstrates that, of course, this is a visual example, but I'll show you some other example later. Usually, this kind of judgment is actually quite subjective. And if I ask you to explain, you might come up with a reason, but I'm pretty sure that, except for simple examples, right? If you ask two people who actually are, even if they arrive at the same conclusion, if their explanation will be different, right? So why do you think this coin, essentially if you know this is coin, so this is, later I mentioned, this is actually called unsupervised learning, where you don't have any labels, okay? You actually need to rely on some other mechanisms to work out the final results. But anyway, I mean, we still call them coins. So the coin and the seashells are actually very different. So if you want to group them into two groups, basically, I think everybody here actually agree with the answer, right? Now, if you want to explain why, right? If you look at the seashells, they are actually quite different as well, right? So based on how you answer these kind of things, there are this actually corresponding to different views of this kind of clustering. Later, when we talk about a few typical clustering algorithms, you will actually have a much better idea. And also, what if I ask you to group these objects into 3 clusters? 2 is easy, right? 3 is not easy. And I don't think everybody will agree on the same answer. Okay? So just through this example, you already see there are a few distinct differences. Okay? But the general idea is that once I arrive at some kind of grouping, let's say, just for the sake of easy illustration, let's say everything here is cluster 1. Everything in the middle is C2, and this coin is C3. So that's a set of objects. Then it's relatively easier to verify, or at least to compute certain measure, qualifying whether this kind of grouping is good or not. Okay, that's usually the case. It's not always the case, but in the actual applications, I mean, clustering actually have multiple applications. But some of the applications, for example, in business, they actually do so-called custom segmentation. So you want to figure out, based on all the information and the purchasing patterns and all the interaction with the customer, you want to categorize your customer into different categories. One very distinct example is actually for telecommunication companies, right? So there are customers, if you think about any, let's say, Tesla or TPG or Vodafone, you actually got, there are certain group of customers which are easy. For example, they only use internet, right? They do not use mobile phone or whatever. But let's say even within those, customers who actually only use a mobile phone, let's say, essentially, there are very diverse patterns. I mean, there are cases where you actually you only have a fixed number of friends, and you actually use it very frequently, but you rarely call other numbers, right? But there are also cases where there are lots of other calls. So understanding this, I mean, before you look at the data, you actually do not know how many different kind of customers you have. And also, this kind of how different is really subjective. I mean, I just come up with a few like common sense examples, but I'm pretty sure that if you work in the industry, right, each company might have their marketing strategy or goals, whatever, to reach. So basically, their view of this kind of clustering result will actually be different. So at the end of the day, I mean, either you can come up with some kind of automatic, let's say, automatic means it's an algorithm, or by computer they can actually automatically evaluate some kind of number to give you some kind of quality of the clustering, or you can actually hand it to the user. Let's say, for example, the manager or business analyst in the telecommunication company to figure out whether this is what you want. Okay, so this is actually quite different from, we haven't talked about classification, but for classification, usually you are given certain very clear, we actually call the ground truths. Ground truths are not necessarily always correct, but we do believe that they are mostly correct. And so this enables you to automatically configure your algorithm or whatever system to achieve the best possible outcome. But for clustering, usually things are a little bit harder. So we either find some kind of proxy, we usually call the proxy measures to automatically evaluate the quality, or we actually need a user. So this is actually another example. So this is actually not, right, although this is still image, but you can actually think they actually represent a slightly different case, right? So let's say if we want to group them into two groups. So this is actually not as straightforward, right? Of course, I mean, I think many will have certain immediate idea. For example, you can group along the gender line, right? Or you can actually group using whether they are wearing glasses or not, right? And so just quoting on these two criteria, can you combine them, right? So why don't you just only look at one criteria? You can actually say, based on some kind of overall consideration, considering all these kind of things, we actually decide, okay, blah, blah, blah. So, so there are a lot of ways to handle this problem. I'm just talking about one way is actually this kind of way. So this is actually similar to what I said. You actually come up with some kind of criteria. Usually it's actually depending on so-called features. So here we haven't talked about classification, where we actually do have a formal definition. But for now, it suffices to say that for each and every object, think about these are customers. You actually extract same number of features. Okay. So one of the feature, usually the feature can be represented in this kind of tabular format. It's very similar to a relational database. So actually, one of the things we actually talk about data warehousing is that once you actually have this kind of data, it's relatively easier to do whatever data mining or machine learning on top of that. Okay. So here you can see that we can extract gender, wearing glasses, having mustache or not, is he or she smiling or wearing hat or not, right? If you observe more carefully, based on their clothing or whatever, you can have additional attributes. So in both in this kind of unsupervised machine learning and in supervised machine learning, which is classification, usually in the traditional field, we are not talking about deep learning, it's your job, it's the model designer's job, trying to come up with a set of attributes, okay? And depending on different kind of models, some of the models actually can handle a large number of attributes. For example, in, again, yeah, for example, if you have to deal with documents, we haven't talked about this, but in the classification part, we'll talk about documents. One typical way that you actually use each and every word in the document as a feature. So if you have a collection of documents and you need to do clustering, right? This is actually very useful if you want to let's say, automatically group the documents into different, for example, we are researchers, so we might be given a lot of research papers, and you want to automatically group them into different clusters. So you can actually come up with different kind of attributes, and each of the objects then can take certain values of these attributes. So here, we actually, it's easy because most of the attributes are actually binary, but there are actually, because yes or no or male or female, but there are cases where it's more than one value, and we'll talk about a few representative data types later when we talk about how to pre-process the data to perform the clustering. Another kind of thing is that the data might be noisy. This is actually especially true in clustering because unlike classification, where relatively speaking, data are actually cleaner. Okay, but for clustering, we don't have any. You can assume that we don't have any knowledge, we don't have any supervision. So users do not participate to give you certain guidance, and hence, even if the data is actually wrong or contain obvious problems, there are different kind of problems. There are erroneous data, or this current object is simply an outlier. We'll actually have some example in the classification part, where, for example, if you think about all the mammals, right? If you know, almost all the mammals give birth to their next generation, right? Just like humans, cats, or whatever, dogs. But actually, there are very few mammals. For example, in Australia, we have this kind of platypus. Basically, they actually lay eggs, but they are actually mammals. So you can think about this is, for whatever reason, the scientists actually define platypus as mammals. So basically, you have to, obey this fact. But then you can actually see that this is actually not your typical mammal, right? So that's the thing. So here you can see that one very simple thing, that for object 5, for this guy, it's hard to say whether he is smiling or not. So basically, you might have some kind of missing attributes there. Okay, this is just one example. There are also a lot of we used to have a data pre-processing module where we talk about the data quality problems, but most likely this term we probably won't have time to cover it. Okay, so the rest are actually all these kind of applications, but there is actually another way to deal with this kind of clustering. Okay, this way of clustering is more like very scientific, right? It's not scientific. It's more like very mechanical. So like you actually define some kind of things, and you work out a way to extract the attribute values, the feature values from each and every object. Okay, so this is pretty generic, but this actually require you to represent each object with very precise informations. Okay, but it turns out that for clustering, we don't really need that. Of course, with that, you can actually perform a lot of clustering. But for certain kind of clustering algorithms, all they want is actually to try to see whether the two objects should belong to the same group or not. Right? So given any two people, let's say your friends, if you participate in different kind of groups, you can actually immediately know whether these two, at least you have a mental model to predict whether these two people will actually sort of be good friends, or at least compatible, or work as a team, or whatever, right? So you don't really work out for example, his ability, come up with, let's say, his different kind of ability and so on and so forth, and use a particular, like a very static formula to work out some number, okay? But somehow you actually can use some other whatever things. For example, you observe a few times when they are actually together, or let's say work as a team, and whether this succeeded or not, or and so on and so forth. You can have all sorts of things trying to find, we sometimes call it similarity, or you can actually find the dissimilarity. Dissimilarity is essentially difference. Okay, so you can actually say, okay, these two guys are very compatible, or these two guys, you should definitely not put them into the same team or whatever, right? So it doesn't matter. So as long as you can give the pairwise similarity or distance measure, or dissimilarity, usually dissimilarity are measured by some kind of distance, okay? As long as you can do that, you can actually run some kind of clustering algorithm. So below, we quickly walk through a few examples. For example, this is very old paper. You can see nowadays, I mean, it's all deep learning things, so it's kind of different. But the general idea that this is actually some real image. Many years ago, my student actually worked on this kind of security. This is kind of security footage. So you have camera facing the lift, which goes into the office, right? So basically, you want to track the same people. So it's called a person re-identification kind of task. Again, the picture is very small. But if you can see, they are slightly different, okay? Because essentially, if you take the same picture from different frames in a long clip, then they are going to different, okay? But the general idea is that if that's the same person, a lot of things are going to be similar, okay? So basically, there are algorithms to detect the bounding box. So there are algorithms to detect this kind of bounding box. If you see a rectangle around people, nowadays, I mean, you actually, if you want to do face recognition, it's the same thing. They actually will put a bounding box around it. And if you ever do some kind of labeling task, essentially you need to put this kind of boxes around. For example, if you want to have some data video tagged for autonomous driving, basically you need to tag all the road sign, road, whatever, pedestrian, whatever things. But the whole idea that there are ways to map whatever pixels within that red bounding box to a histogram. Basically, there are some kind of models. It's actually some kind of color models. I think we use RGB here, but I mean, the example is just use RGB here, but there are actually different kind of color models. We won't go into it. But basically what you do is that you actually come up with a feature, say, okay, roughly speaking, let's say the first bucket is all the reddish pixels, let's say. So there are actually certain things you say, because RGB, then basically the red value should be between a range and RGB, green and blue, between a certain range. So you actually can compute a histogram. And if you want to identify from another shot, you actually still find the person and from the bounding box. By the way, here I just copy it. I don't have the original one, so I just lazy just copy it. But in reality, this number, for example, this is 40. This could be, let's say, 42 or whatever. Even there are cases where some certain, let's say this is 20, and this one could be as high as 80. Okay, because if the person actually rotates, change the angle, maybe there are some, let's say, greenish color from the back of his shirts or whatever. So you need to admit that they are not identical. Okay, and but the general idea that if the image actually belongs to the same person, they are going to be quite similar to each other, or at least similar to one of the, if you really have the continuous image, right, you have the continuous frame, keyframe captured, so you should be able to, because you can't, in a fraction of seconds, totally change into another clothes, right? It's definitely not happening every day. So basically, there are certain things you can actually say, if I can measure the similarity between them, basically I can do some kind of clustering. Okay, this is another real example from the this is immunological distance. So essentially, what they do is that they got a set of species and they want to work out the evolution path. In fact, we have this kind of COVID 2019, right? So essentially, my understanding that they are doing similar things, trying to trace out where the virus come from, right? So again, this is a very early example, and that they use things that everybody can understand, right? But you can imagine that this kind of things is very useful to deal with the real scenario. Of course, I mean, there could be more sophisticated nowadays. There are more sophisticated technologies, but at least this kind of clustering to find this kind of similarity, and hence can group things into, for example, my understanding the virus DNA, due to a lot of reasons. I mean, first of all, whenever you do the sequencing, there are certain errors. Okay, and also when you assemble the fragments together, there are certain errors, and so errors is everywhere. So basically, even if, and not to mention that the virus will mutate over the generations. So basically, you are not going to see the same DNA, but based on the similarity, whatever things, you can actually see, okay, these are actually all, let's say, COVID-19, and they are most closely related to maybe another virus or whatever. I think I read a report that, for example, the previous pandemic is sort of like a SARS, and there are actually different. There are actually, I think, even for COVID-19, they also. I think I saw reports where they actually found, okay, the virus sample taken from different places, or even different countries, they actually are not quite the same. Okay, so what they are doing is that they actually perform certain kind of experiment. Again, I didn't bother to read the original ones, but the general idea that you can imagine that they actually run some kind of test and see how their immune system actually respond to different kind of things. Okay, I think that's the whole thing. Based on this, they actually work out pairwise. They are able to work out pairwise. For example, this is 38. This actually means, I think this is similarity. So you can see that the dog and the dog is actually 0. So that should be the distance. That's the dissimilarity. So how different they are. Okay, so 0 actually means they are actually the same. So you can see that the diagonal part is all 0, right? And you can see that between weasels and the sea lions, the distance is 38. But between the monkeys and the sea lions, it's actually 142. This means their immune response to certain pathogens or whatever things are drastically different. Okay, so based on this, if you run certain kind of hierarchical clustering algorithm, one of them is, anyway, in biology they actually give all these algorithms different names, but basically you end up with this kind of things. This is actually called a dendrogram. Basically, it shows a tree which hopefully explain the evolution path of these kind of species. Okay, so you can see that here, as you would expect, seals and the sea lions are very close to each other. This number is actually their distance. Okay, immunology distance, and the next closest one is actually bear and a raccoon. All makes sense, right? And then the next is actually basically, yeah, so all these kind of bear and the seals, whatever, are together, then they are actually more similar to the weasels than dogs and then cats and finally monkeys. Okay, so that's what they got. So it turns out that certain parts of the results actually make sense, but certain parts are actually incorrect. So essentially, people actually come up with some other modification of the clustering algorithms. So this also shows that if you don't have, whenever you have the domain expert, they can actually say, okay, the result probably is not the best, and you can go back and modify the algorithm or parameters or whatever, and they come up with another. So it's actually it's called a neighborhood joining tree, whatever. But it's another slightly modified clustering algorithm where they actually produce slightly different results. So I think they believe this actually makes more sense. So you can see that now bear and the raccoon are still together, but next closest one is actually dog. Okay, because previously the seal and the sea lion are actually most similar to bears, which is kind of strange, right? Okay. Actually, there are other examples where they really have a lot of DNA or whatever things. I don't think I showed them. But anyway, there are a lot of clustering applications. So the other thing is that this is actually a Flickr website where you can share photos, and they do have the option to tag each and every photo and tag each and every album, because you can load a group of picture as an album, right? But the problem is that I mean, think about, I mean, most of people do not use it, right? You just drag it, if there are drag and drop interface, you just drag it to the browser, and maybe you just name the album with certain name that you kind of understand. Let's say France, or let's say Paris. But essentially, first of all, you mix a lot of picture together. For some reasons, I mean, you might mix a picture which is not in France into the France. And also, for each and every picture, I don't think most of people will actually bother really to write a description or this kind of, we actually call the metadata for them. So without these kind of things, it's easy for you to just store the picture there. But whenever you want to find, let's say you want to find a picture, let's say when you visit, let's say a particular place, you have to browse. And this is actually, for people with many photos, it's hard. And also from the system perspective, they cannot do too much. Okay, because at that time, nowadays we actually can do a lot directly on the multimedia data. But again, these are very old examples, and by that time, basically processing image are both time-consuming or resource-consuming, and also not that highly accurate. So one of the things you can actually do is to exploit the fact that you can actually automatically assign tags to the photos. Just imagine, right? If you ever went to Paris, there are a few places, let's say Eiffel Tower, whatever, just a few places that you definitely will go. And for whatever reasons, even if you take the Eiffel Tower from different distance or angles, whatever, that's going to be very distinct, right? So each picture are different because the weather conditions are different, the person in front are different, there are tourists going around, but basically they are going to be very similar. So basically by doing these kind of things, as long as one of the user ever bother to tag it, or you sort of manually tag one of the picture as Eiffel Tower, then you can actually automatically tag all the pictures as Eiffel Tower. And then you can support, you can do a lot of things. I mean, at least you can allow user to say, okay, give me the photo I shot 2 years ago, let's say at Eiffel Tower, right? But if you really look at it, there are actually things which are very different from, for example, parade. I think another example, actually, I reviewed a PhD thesis, and they actually do video. Actually, they do. I forgot exactly what they do, but essentially they have a lot of video clips. They need to classify or this. I mean, they need to extract to understand. Okay, this party is about abstract concepts like birthday party, right, or just party. Yeah, here don't have party, but you have carnivals. So if you think about, I mean, or wedding, right? But if you think about it, they are, I mean, the challenge, I mean, that's actually, I think I reviewed the thesis about 2 years ago, whatever. But anyway, I mean, the student actually come up with some kind of solutions. I won't talk about a solution, but the whole idea that even with his solutions, the accuracy is still pretty low. One of the main challenges is really like for wedding, right? Let's say, or for party. You do have a few typical forms, right? Church or whatever things, but you might have other types of party, right? Not to mention that you have different ethnic groups and they do party or wedding in a different way. But essentially what their approach is essentially trying to find a few common concepts like, let's say, candles or flowers or whatever things, right? Or people dressed, whatever. Use these kind of things and together with a lot of clues trying to figure out whether this clip is about wedding or it's about, let's say, football match or whatever. So anyway, so this kind of for this kind of parade or carnival, whatever, it's actually very diverse. So this kind of clustering algorithm is still very hard nowadays, I would say. Of course, nowadays we have more and more resources and the methods trying to do it better. So I won't go in detail over all the other examples, but suffice to say that there are lots of direct use of the clustering methods. Of course, I mean, most of them are actually old examples. Nowadays, there are lots of more. I also want to quickly mention that in the project, you will actually see that we actually use clustering to do something totally have nothing to do with clustering. Okay. there are actually a lot of applications where you can use clustering to either as a pre-processing or as ingredients to more complex models. Okay, so basically, yeah, we won't talk too much about it, but there are actually lots of things you can actually do. For example, even in the classification, we haven't talked about classification, which is supervised learning. In practice, you actually need to deal with the case we actually call it. There are different names. There are actually semi-supervised learning. There are like active learning or whatever. I mean, basically, certain solutions to these harder problems actually require you to do certain kind of clustering. Okay. So what is clustering? So basically, a cluster is just a group of objects. Okay, you just do some kind of grouping, and with the overall goal, it's actually two goals. One is similar to each other within the same cluster, and dissimilar to in other cluster. So this is actually intra. Sometimes you see intra-cluster, and this is inter-cluster. Okay, so you want high differences or dissimilarities inter-cluster. Okay, but you want high similarity or small distances intra-cluster within the same cluster. So usually, whenever you have more than one objectives, it's almost like you want to enjoy a very good dinner, but you only pay very little, right? Usually, it involves some kind of compromise, and it's usually not the case that you can achieve both. Okay, so basically, you can see that different algorithms actually try to. They don't really. I mean, some of the algorithms don't explicitly mention this, but some of the algorithms actually are actively. Put more emphasis or more directly optimize one goal, and in the meanwhile, they also try to make sure the other goal is not too bad, and so on and so forth. Okay, there are different kind of trade-offs. So the so-called cluster analysis is to group a set of objects into clusters, and the cluster belong to unsupervised classification or unsupervised learning. I would say unsupervised learning. So basically. You don't have any user supervision. So you don't have any label, you don't have any whatever knowledge on the data. So you actually need to deal with these kind of things. And there are, as I said, I mean, you can use it as a standalone tool, or you can use it as a pre-processing step or some other ingredient parts to other more sophisticated kind of algorithm or systems. So there are a lot of usage. We'll just skip them. As I said, I mean, what is a good clustering? Basically, you need to have high intra-class class here is the cluster similarity, and the interclass low interclass similarity. We already mentioned all these things. So there are actually a lot of requirements or challenges. One of the things, I just pick a few things to give you some example. So scalability is actually the number one thing. In fact. Even nowadays, I mean, if you are dealing with really large data sets, there are only very limited number of clustering algorithms you can use. I mean, of course, there are always ways to use an algorithm based on a few approximation or reduction techniques, mainly the sampling. Okay, but most of the clustering algorithms, are very expensive to run, except maybe k-means. So that's actually one of the reasons. The k-means, which is the first algorithm we are going to talk about later, it's going to be the most popular one, and it's very simple to implement and execute, and it's fast enough, and you can stop it at any time. Okay, so there are a lot of good things, but scalability is definitely not cheap. Okay, the other thing is that you need to deal with different type of attributes. Okay, we'll see some concrete example later. The third one is discover a cluster with arbitrary shape. Not every clustering algorithm can do that. It really depends on whether, again, this is actually in low dimension, or when you actually have pre-knowledge, you can actually say, okay, my cluster should look like whatever. Usually you see the example like 2D example, so you can 2D or 3D, you can visualize it. But in real high dimensional space, we all know that cluster are not going to be spherical. It's not going to be like a ball or even a eclipse or whatever, or ellipse in high-dimensional space. But unfortunately, most of the efficient algorithms rely on these kind of things, trying to speed it up. So there are how to discover cluster with arbitrary shapes is still not very clear. In fact, I mean, the shape itself in high-dimensional space is very different from our low-dimensional intuition. Of course, I mean, this is there are parameters. I just want to talk about this one, the ability to deal with noise and outliers. So this is actually another very, I would say, probably scalability and the noise and outliers is actually are the two main things you need to consider when you choose a clustering algorithm. I mean, all the other things are relatively easier to deal with, or you can live with. But basically, some of the algorithms, let's say k-means, they are actually very bad with outliers or noisy data. As long as you have some kind of noise data, and if the algorithm is not robust enough to handle these kind of things, there are actually robust version of k-means. Basically, I mean, even some one data points might screw up at least a big part of the clustering results. Okay, and this is actually more prominent in clustering. Another reason is because, as I mentioned before, it's unsupervised. So users don't even have don't even necessarily need to look at the data, and because if you look at data, you might realize, okay, something must be going wrong. Okay, basically you just throw a bunch of data to the algorithm, and the algorithm really need to be robust to deal with all sorts of things. So what we are going to do next is that we are going to look at how to what are the typical inputs and how to deal with different kind of types. So this is one of the requirements of the clustering, and then we hopefully today we can move on to the k-means clustering if time allows. Okay, so first let's look at the problem, how to solve the problem using computers, right? So basically, we already mentioned that there are two typical kinds of inputs to the clustering problem. One is actually called the data matrix, the other called the dissimilarity matrix. Dissimilarity is essentially distance, but sometimes you can actually put a similarity matrix as well. It doesn't matter as long as you know that basically if it's a similarity matrix, a smaller value means they are more similar. If it's a dissimilarity matrix, a smaller value actually, if it's a similarity, a smaller value means they are not similar. They are quite different, right? And for dissimilarity matrix, a smaller value close to 0, let's say, it actually means the two objects are very similar. So the two input format actually differ by, you can notice this easily by the dimension. Okay, so whenever you have a matrix, it's essentially you have how many rows and how many columns. So the first data matrix is actually in general called n times m, which means there are object 1 up to object n. So you have n objects. Usually n is number of objects, and each one actually have m features. You extract m features. So for the first object you have x11 and up to x1m. So one concrete example is the smiling mustache gender whatever example. So this is the case where it's encoded. The input is encoded into this kind of data matrix, and we already see that essentially you need to define the features, and sometimes you even need to write a program to extract the features. Okay. Yeah. One of the problem we actually worked on several years ago is actually called co-reference resolution. Basically, for example, if I give you a lot of documents, news documents, right, and you want to group all the documents talking about the same person, let's say same mention essentially, or the sentences mentioning the same person, let's say Donald Trump, right, into the same cluster. Okay, so that's the requirement. But the problem is that because it's coming from different documents, so this document might be saying, okay, Donald Trump met French president or whatever. And the other one is actually talk about something else. So how do you know this Donald Trump is the same as the other Donald Trump? Right. So the general idea that you need to use some kind of data mining and NLP, trying to get the surrounding, trying to look at the semantics and finding the similar. So essentially, it all boils down to pre-process the documents and all the context, finding the right context. There are a lot of details there. But basically, if the dimension, the context semantically are similar, at least in some way similar to a typical Donald Trump, let's say there is another Donald Trump. Let's say Michael Jordan, right? Michael Jordan could be a basketball player or could be actually a professor in Berkeley, and maybe it's a very common name. So definitely there are hundreds of Michael Jordan there. But basically, based on their interactions, I mean, if you really have a context mentioning this person in a document, in many cases you can actually correctly identify, okay, this document's Michael Jordan is not the other Michael Jordan. Okay, so basically you need to represent these kind of things in this kind of thing, in this kind of feature. Oh, by the way, because we haven't talked about the clustering classification, each row is actually a transposed feature vector. Okay, in classification you will see it more formally. Essentially, we actually represent the object O1 using this kind of row vector. Okay, you can go back to the picture example to give you a concrete example. But basically, from now on, everything we do, we can forget about this as O1. We only need to look at this vector. Because essentially we need to have some kind of mathematical background, grounding to work with. As you probably know, in machine learning or this kind of data mining, typically we use vectors. There are actually even more complex objects you can use. But usually we deal with vectors and relations, matrices. For example, when we talk about spectral clustering, even for graphs or trees, whatever, right? Graph is a very general data structure. You can represent this using a matrix. So as long as you can manipulate the matrix, whatever, basically you can do a lot of things. Okay, so this is feature vector representation. The other one is actually similarity matrix, which I already mentioned. That's the immunological distance. Okay, in that case, it's the distance, so it's a dissimilarity. So usually this is n by n, n being the number of objects to cluster, right? So it's a square matrix, and for most of the distance or dissimilarities, if you think about usually this dissimilarity is actually the distance. Although it's not always the case, there are actually certain measures which are widely used. For example, the KO divergence. It's not a distance measure, but it also measures the difference between the two objects. But it's for KO, it's actually asymmetric, which means the distance between A and B does not equal to distance between B and A. But we mainly deal with the symmetry case. Okay, but I just want you to know that there are reasonable and very useful distance and applications where the distance is not symmetric. There are also cases where the distance function is actually, we call it non-metric. We'll talk about metrics in a few slides down. So there are all sorts of weird cases you need to deal with. But basically, if the distance is symmetric, so basically we know that we don't need to, the reason we don't write this one is that this one should be D12. D12 is the distance between the first object and the second object, or to the second object, and the D21 is the second object to the first object. But in most cases, the distance is symmetric, means they are the same. So basically, you can represent everything using a triangle matrix. So it could be up triangle or lower triangle, it doesn't matter. Actually, we already have an example in the cat, whatever COC line example, right? Yeah. So the next we actually talk about one of the requirements to deal with different kind of attributes. So we actually look at a few common ones. For example, the first one is interval valued variables. So in simple words, these are usually some kind of measure. It's a numerical number, and the number is usually bounded. okay, between certain values. So what we do is that we need to standardize the data, but in many cases we also say we need to normalize the data. By normalization, essentially, we really want to bring the data value in different attributes or in different features to be approximately within the same range. Okay, so if you look at this representation, we really want to make sure that, so this is our column, okay? The column, by the way, this is actually also called a design matrix in classification, okay? So the column in that matrix, essentially each column is a feature. So you can think about this is the weight of a person, and this one is the height of a person, right? Now, if you think about, I can represent the same thing, I mean, there are other attributes, using different units. For example, for weights, I can use a kilogram, right, which is by default. For heights, you can use meter, right? That's almost like the default one. But if you think about the kilogram, I think even the leanest person here weigh more than 40, right? I mean, otherwise it will be really, really skin tight, right? So basically, but nobody is actually 40 meter high, right? So the whole idea is that all the value in the first column is going to be very large. I mean, it's not that large, but compared to the height column, the value is going to be very large. For height, I don't think anybody here is actually more than 2 meters, right? So it's usually between 1 point something to 2. So it's within a small range, but the weight can vary much wider, right? And also absolute value in terms of weight is very large. So this will cause a lot of problem. Later, when you look at the real problems, all the algorithms, you actually see that if you don't do anything, just take the value at the surface, I mean, just take the given value, basically the column or the feature which have large absolute values or large range will dominate the whole process, right? Because, I mean, later you'll see that we measure some kind of distance, we need to compute some kind of distance. The simplest approach is that, let's say this is 50 kilo and 1.6, right? And the other guy could be 80 kilo and 1.8. So basically, whenever you do, is that you actually calculate by default. Usually we use L2 distance. That's almost like the first thing you want to try in most of the cases, especially if you know little about everything else. Basically, you can see that the distance is mainly determined by the difference in the weight. So think about the 2 points. One point coordinate is 50, 1.6. The other one is 80, which is much to the further right, and the 1.8, which is slightly above. So if you do the measure of the distance, it's actually dominated by the weight, right? So this actually will cause some problem. So basically, our goal is trying to normalize them into the similar range. For example, everything is between, let's say, 0 to 1. There are actually methods which just scale the smallest one to 0 and the largest value to 1. But this might cause a lot of problem. Especially, this is actually doable actually in classification, where relatively speaking, the data set is more clean. For clustering, in real problems, you have outliers. You have noisy data, whatever. So essentially, if an outlier, for whatever reason, for the height, if you forgot the dots, decimal point, right? This person is actually 1 point, let's say 56, right? And if you forgot to type in, you thought you type in the decimal points, but you didn't, then the number becomes 156, right? So then you scale this number to 1, and then almost everybody else will actually have 0 height, right? So taking that into consideration, that's why when we do the standard deviation, I mean, when we do the normalization of the numerical data for clustering, essentially we do certain kind of normalization like this. So this is the original value for the eyes objects, and F is the feature. Let's say this is height. So F, you can kind of ignore F if you only concerned with only one attribute or one feature. So what you do is that you each raw value, that's the raw value, is is actually subtracted with a mean. Actually, this M is the mean. So you can actually see MF is essentially the mean. This is a arithmetic mean. And so you actually remove the, so you, in other words, I mean, if you do something like this, sometimes we also call it center the data. Center data means, okay, after you, if you don't do the scaling, this is the scaling part. If you don't do the scaling, if I give you the data, if you take the average, it will actually be 0. So that's why it's called a centered. If you plot it, roughly speaking, I mean, it's the geometric center or whatever, it's actually at the origin. So it's not biased towards one side. Okay, so it's actually center the data. And then you actually need to do some kind of scaling. And a very common way to do the scaling, which is widely used in classification, is to use the sigma, which is standard deviation. So basically, this is based on the fact that many of the, I mean, it's not always the case, but in many cases, the measurement takes a Gaussian kind of distribution. And the reason it takes a Gaussian distribution, part of the reason is actually related to the so-called central limiter theorem. So if a measure is actually determined by a lot of factors, and I mean, informally, none of the factor dominates the whole thing, basically the distribution looks like Gaussian in these kind of things. Okay, so it's not always the case. There are also some kind of naturally occurring distribution, like exponential distribution or whatever. I mean, if you learn the queuing theory, whatever, it's actually based on the Poisson distribution, all these kind of things. But the whole idea is that, at least from statistics, I mean, Gaussian is really very widely used and sort of it has very nice properties. Okay. Yeah, I won't go into the details, but basically we don't use the sigma because in order to estimate this sigma, essentially it needs to have the variance. Okay, and the problem with the variance, the formula is almost like take everything to the square and then take the square root. Okay, take the square root outside. But the problem is that with the square, as long as one of the value actually like become 165. The average will be something like, because only one guy is wrong, everything is right. Let's say the average is 1.6. Then basically you raise it to the power of 2, it's going to be a very large number. Okay, so basically this sigma will actually be very large. So that's why we deliberate not to raise to the power of 2. So we just use the difference between each and every value with the mean value. So that's the absolute deviation, if you like. And you take the average. Again, there is no square root. Okay, so this SF is essentially the first order of the. You can think about it, it's like the first order cousin of the standard deviation. Standard deviation is actually looking at the second order. Okay, so that's the only difference, and it's actually more robust than using the standard deviation. Okay, so that's for the numerical value. Yeah, let's have 10 minutes break. Then we move on to once we do the normalization, we can define the distance for them.
Is the second lab released?
I think it's. Yeah, the tutor actually sent me something. I think it should be soon, or if it's not, then it should be soon.
Okay.
Let me see.
There was a link available, but when I clicked on it,
It's not working.
Yeah, it didn't work.
I think that the release date will be 9th of March.
That's today.
Yeah. Okay. Actually, the tutor was stranded.
Yeah. Oh,
So
okay.
there might be some time zone difference. So
Okay.
yeah. Just tomorrow morning should be there.
Oh, cool. Yeah, second lab.
Oh yeah.
If not, then let me know.
Okay.
Or just actually the tutor can watch the. I mean, ask him to watch the forum. So sometimes we also make error. We thought we release it, but link is not there or whatever.
Okay. Okay.
don't worry. It's on the way.
Yeah, no worries, no worries. Thank you.
No worries. So what's up?
Just don't quite understand object.
Oh, okay.
Yeah.
So which part puzzles you most? I mean,
It's just this.
why we need to do projection
yeah,
or how to do the projection?
What does the projection do? That's the reason.
Yeah. So can you scroll?
Yeah.
So I think I mean, different people actually have different way of thinking. I found most people actually can deal with this kind of geometric things. So if you run this pseudocode on this toy example on a 3D where you know what should be the answer, you will actually see that if you don't do the projection, you end up with only this one. You're actually missing all the top piece. All the top piece you can actually figure out what exactly it is. It's actually involved. For example, all the again, it's if you imagine this is the top piece of this one, all these fringe are actually the aggregates on this plane, if you like. So you don't have any aggregation along this dimension.
What about that? Which part did you generate that?
This one?
Yeah.
This one is actually done by a recursive call of the PUC.
Oh, sure.
So you don't, I highly strongly suggest that you don't, because that's why we start with 2 dimension. So the whole idea that, think about it, this is like a contract. So if you call this algorithm, it's guaranteed to be producing all the possible aggregates where in 2D it's going to be like this, in 3D it's going to be like this kind of three-way cover. So that's given, just like the proof by induction. So if we assume that you can actually do all different things up to dimension of, let's say, k, now you actually say, okay, now I can do k plus 1 dimension. And as I can do k plus dimension, I can do k plus 2 and so on and so forth. I can deal with all the dimensions.
Okay. I'm just trying to run this pseudocode on the 2-dimensional.
Actually, the level will actually be on this one. So we already give you the skeleton code that you can actually see.
Cool.
Yeah. Actually, I think in the notebook there is like a readily. It's okay. I think if you check out the notebook, I forgot the which one. I don't have time to explain the notebooks, but presumably you can grab what you want. We already implemented this one, and you can see that we try to closely follow the pseudocode, so you can actually see in Python the code is almost like similar to this one. So,
Okay.
And then you can insert breakpoint or print out something, which I highly suggest you do to understand what's going on.
Cool. I'm just not quite understand this part. I already understand this.
So I think if you can take on the geometrical view, you will realize that you have to do this part because you have to do application along that dimension. Everything you've done here is actually on the same slice, nothing across the slice. So you are missing some kind of application.
So you generate this green part through this
projection
here.
Then you can see.
Run that.
Yeah, you run the POC again.
Oh, sure. And then
so it will give you the blue part. Together with the green part, you stack on top, and that's everything.
Okay, cool. That makes sense. Thank you so
No
much.
worries. Okay, let's resume. So for these kind of basically numerical values, after doing the normalization, basically most of the data are going to be in a small range. Okay, you can see that it's definitely, let's say, between -1 and 1 or -2 or 2. It's actually kind of similar to the Gaussian distribution where you could have values which are still very large or very small, but essentially it's going to be, in terms of density or probability, it's going to be very small. So most of the data are going to be concentrated, for example, for Gaussian, 99% of data are going to be within -3 sigma and +3 sigma. So you don't have such guarantee here, but they behave similarly. Okay, you might have more data outside, let's say, -3s and +3s, because this is actually more heavy tail than Gaussian. Most likely most of the real data are actually reasonable data within a small range. Then what we do is that we need to measure once you process every column in the design matrix, like in the object matrix, in this way, then we can actually simulate or sort of calculate what's the similarity or distance or dissimilarity between any two objects. This is usually required in most of the algorithms we are going to talk about. So how to define the distance? So because they are all numerical data and normalized into sort of like a similar comparable range, the most popular choice is sometimes we call the LP norm of the difference vector, or sometimes we actually just directly call it the LP distance. P is a parameter. Okay, there are some kind of reason calling this one, but we won't go deeper into it. And this is also called the Minkowski distance. Again, I think LP is more common. So the technical definition between the ith object and the jth objects is to find their corresponding vectors, xi and xj. So xi is the row vector corresponding to the ith row in the matrix, and the jth row in the matrix. You take the vector difference, which still give you a vector, right? This will also return a vector. And whenever you have a vector, you can take, this is actually the norm. This is actually the LP norm of the difference vector. Okay, norm intuitively measure certain length of a vector. Okay, so the usual L2 norm is essentially the geometric length. But you can actually define L0, or there are even more complex norms. And the concept of norm is actually much widely applicable. I mean, it's more general than the length. But you can think about this as some kind of length. And so the piece norm of a vector of z, the reason I call it z is because after you do this, you can actually call the difference as z, is that you take each and every coordinates dimension values of the z and raise it to the power of p. And because p could be a numeric number. It could be 3.5 or something, okay, although it's not very common. But p could be an odd number. So in order to make sure that, because later we need to do the sum, okay, we need to make sure that if it's, let's say p equal to 3, if you don't take the absolute value, then there will be a problem. The distance will cancel either off. So basically, we take the absolute value, raise to the power p, sum them together, and then to get rid of the effect of the p's exponent, we actually take the p's root of the sum. Okay, so that's the LP norm of the difference vector. So we start with the familiar case where p equal to 2. This is actually usually called L2 distance, or we just usually call Euclidean distance. So that's really the distance between any 2 points in, let's say, in 3D space is really like the shortest distance, the line distance between them. And this generalized to high dimension as well. Okay? But we also have p equal to 1. This is actually called the Manhattan distance or city block distance. So if you think about a point, this is, let's say, 1, 8, and another point which is 2, this is 2, let's say 2, 2. The distance is essentially, going down here and going up here. So the reason it's called Manhattan distance is that if you look at the street, I think avenue and the street, they are actually just like this. So it's divided into clear blocks. So whenever you want to go from one place to another one, you actually need to walk certain avenues and then turn to certain streets. So the total length of this walking distance is the L1 distance. In contrast, L2 distance will be the, sometimes we call it bird, I forgot what's the word, but basically like if you are a bird, you can fly directly over in the space directly towards the destination. So that will actually be the L2 distance. There is a very special one called p equal to infinity. It's the it also defines some kind of distance, but you actually need to use a limit or whatever. But the definition is actually much simpler. So this is actually the largest difference between any of the coordinates of the 2 points. So in this case, for example, for these 3 points, so the green one is the L1 distance, the dotted red one is the L2 distance. The L infinity distance is, look at the coordinate difference. So if you look at the coordinates, so this is 1, this is 2, the difference is 1, right? And this is 8, this is 2, the difference is 6, so it's 6. So the distance will actually only be this one. Okay, so you can see this is the maximum of the coordinate-wise distances or differences. Usually you use this one. This one is actually appears in certain areas. This one is actually very important in certain kind of theories because many problems actually can be solved either in the usual L2 norm or you can reduce to L infinity norm. This is called the L infinity norm. And in fact, this defines a very strange kind of space, and there are a lot of mathematical results there. But usually you don't encounter this. Okay, so apart from these kind of things, we also have other distances. Okay, so the one I just want to quickly mention is Jacquard. Jacquard is not a distance; it's a similarity. Okay, but there are ways you can convert this into distance. Jacquard is actually widely used because usually I write a J, right? Jacquard is actually between 2 sets. So these are sets. Sets you can write in this way, right? So you have elements here, 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 here. So it's actually defined as the intersection size over the union size. So this is actually a mathematically wide, almost like the default definition to measure the difference between 2 sets or 2 groups of people, right? So if you look at this, the intersection essentially says how many elements are in common in both groups, right? In this case, in our following example, it's going to be 2, right? Just these 2 guys, this guy and this guy. And then the union is essentially the union is actually A plus B minus A intersection B. Okay, you can prove by yourself. So basically, if I know the A is 1, 2, 3, 4, 5, the B is 1, 2, 3, 4, 5, 6, 7. So that's going to be 2 over 5 plus 7 minus 2. That will be the union size because the common elements was counted twice, right? You remove one copy. So basically, the Jacquard is actually guaranteed to be between 0 and 1, where 1 actually means the 2 sets are identical, and the 0 means they have absolutely nothing in common. Okay, so this is a very intuitive measure, and we are going to see some usage of it very soon. And there are also other kind of things, and there are even distance functions which I said KO divergence or other kind of F divergence where they are not even symmetric. Okay, so there are even weirder distances. There are also distances which are defined by dynamic programming. So if you know edit distance between two strings, if I give you two strings, for example, if you want to find the approximate matching of the names or whatever things, you can use edit distance, and its computation actually involves a computation. I mean, to compute the edit distance between two strings, you actually need a sort of like a non-trivial algorithm to do that. It's actually based on dynamic programming. So basically, for all the distance we are going to talk about, usually we actually deal with so-called metric distance. And this is actually, we want to emphasize this point, but I'll quickly illustrate why this is important. Because without this, if you are, just in case you are dealing with a case where the distance is actually not metric or not symmetric, then you should really pay attention to whether you can use some of the existing algorithm or not. In that case, many of the algorithms internally will break down, okay, or they'll give you very weird results. So the matrix distance, anyway, essentially says, okay, the distance function between two objects or 2 points or two whatever objects satisfies all the 4 definitions. And the first, if you look at definitions, the first 2 are actually very simple. It just says distance is non-negative, right? This corresponds to the intuitive idea. If I'm talking about distance, what do you mean by, okay, these 2 points have a distance of -1, right? It doesn't make any sense. And additionally, it's only 0 when it's, so it's only 0 when you are comparing the object with itself. Right? It also makes sense. You don't want to say, okay, the difference between me and myself is actually 0.001. Even with the small thing, if you accumulate error, it's going to be the first copy of you and the last copy of you will be very different, right? So this one is the symmetric. So this is a symmetry. So basically, distance between I and j should be equal to j and I. It's not always the case. For example, think about the road network. So there are plenty of one-way road around, even in the campus. So sometimes you go from A to B is shorter than you go from B to A, if you drive especially. So basically, but in most cases, we don't do that. And the last one is the unique one. Some unique one in terms of metric space or metric distance. This is actually called the triangular inequality. Okay, so what it means is that so if you have just a point A and a point C, right? So I don't know what is the distance between A and C. So the why we need to have this kind of triangle inequality? This means, okay, if you know some common guys, let's say I call it B, you can think about this as the landmark. Sometimes we call it pivot. There are different names. You can think about they are common friends, okay? And you have this one and this one. Basically, then, let's say this is 3, this is 5. Then you know this guy is smaller or equal to 8. Because you need to make a triangle, right? The length of 2 sides of a triangle is going to be larger or equal to the other side, the third side, right? Otherwise, you won't make a triangle. There are distances where they don't obey these kind of things, okay? But anyway, most of the distance we talk about actually satisfy this kind of condition. And not only you can say the distance between A and C is greater or equal to 8. You can actually put a lower bound on their distance. These 2 points cannot be too close. What's the lower bound? Yeah, it's 2. It's actually the difference between the 2 sides. Because if you can draw it in another way, I think it should be, let's say this is B, this is C, this is A, right? So this is 3, this is 5. So the distance is at least 2. It can't be too close. Okay, so this is actually the the major, I want to write it in mathematical forms. Essentially, you can figure out we only write in one way, but you actually rearrange the term, you can actually have the other side. But the key point here is that if the distance actually satisfies the triangular equality, as long as I know certain distance information towards some kind of common guys, you actually can put a good estimate on the minimum and the maximum distance between any two objects. Okay? If you think about it, it's almost like, in reality, there are a lot of things like agent or whatever. The whole idea that it's actually connected to many guys, and basically they can actually give you some kind of distance, even if, let's say, this person and the other person never met, but basically with the information about you and some common objects and the common objects with the other guy, you actually can work out some kind of distance. Okay, so this is useful to make sure that, for example, this AC is smaller than 8, right? I removed the unnecessary part. So the general idea is that if for some reason I actually put A and B into one group, right? Now B says, okay, I have a very good friend, okay? C is the small, among all the other points, there are other points, D and E, whatever, which are further away from me. So C is my best friend, right? Except for A, okay? Can I invite him to join the group, right? So the distance is 5. So the whole idea is that if distance is small, right? In introducing C into the group does not increase the maximum distance between any 2 points in the group by too much, because you still have an upper bound on how different they are, essentially. But if the triangular equality doesn't hold, which means even if 3 and so in reality you can see that even if A and B are very similar, B and C are very similar, A and C could be totally different. You can't even put them into the same team, right? This is also possible. This is the case where the distance is not metric, so you don't have this kind of bound, or sort of like peace of mind. So that's the roughly some idea on why this is kind of important. Okay. The other thing is that we can actually visualize all the effects of the LP norm. This is arguably the most important kind of distance. So you can actually see that given any points in the middle, and you can find all the area where all the points, the L1 distance between Q and X is smaller than or equal to 1, let's say unit distance. Then, if you use L1 distance, the shape will actually be almost like it's actually a square, but it's like a diamond kind of square. And for L2, it's a circle, right? Everybody can understand. Again, I showed this in 2 dimension. In a high dimension, circle is still become a sphere, which is simple to understand. But L1 in high dimension is kind of strange. You can think about it in 3 dimension. Okay, so it's kind of it's not just a prism out of the paper. It's actually slightly different. Again, I draw something between 2 and infinity. This is actually not exactly right because I use a point, and that's the best thing I can draw. But basically, you get the idea. Basically, we look at L infinity. L infinity will actually give you a square, but this time it's much larger. So if you put this on top of L1, it's going to look like this. So the outer rectangle, the outer square will be L infinity, and L2 will actually be the inscribed circle. And you can imagine that L8 is something like this, right? A more fatter version. So this is something like L8. Okay, that's the best thing I can draw. Actually, there are something like let's say L 0.5. You can actually imagine what the shape looks like. In fact, this is actually not a ordinary norm, or it actually will give you a concave set. So all the set here are actually convex. Convex means given any points, any 2 points within this shape, right? You link a line, and any points on the line are still within the set. Okay? Whenever you have a concave, let's say this is concave, right? You can have a point here. You draw a line. This point is not inside the whole thing. And another concave, I mean, if you try this one, it will give you a concave shape. Okay? Yeah, and just remember that convex is much easier to deal with. Concave is, I mean, non-convex things are much harder to deal with. Okay? The other very common type of variable is actually binary variable. We already seen that. So binary variable takes only 2 values. So there are 2 cases where the first case is that the binary variable is actually symmetric. Symmetric means, roughly means, for any objects on this attribute, right, or on this feature, you don't think the true value, that the probability of taking one of the values will differ too much. For example, gender or whatever things. If there is a substantial difference between the probability of a random object taking one value over the other one, then you actually call them asymmetric. So one typical example for asymmetric is actually some kind of test results in, let's say, in medical domain. Whenever you do some kind of blood test or whatever, you really want all the results to be negative. Negative means there is no blood, let's say there is no virus in your blood, there is no too much growth of white cells or whatever. I mean, all sorts of biomarkers. You want them to be, in medical domain, negative is actually good. Positive actually means something abnormal happened. And so basically, the symmetric and the asymmetric case are dealt with differently. So for the symmetric ones, the formula is actually something here, but this rough just says, okay, look at how many cases they are different. Okay, to give you one very simple example, look at these two objects, and it's very similar to the cartoon face example. So you have different binary attributes, wearing hat or whatever, right? So one is, let's assume that they are all symmetric for now. So what you do is that you need to define how similar or how different these two cartoon figures are, right? So the difference is essentially, I mean, let's say this is gender, they are the same, right? Let's say this is, I forgot which one, for example, wearing glasses. So they are different, right? So difference is actually 1, and this is another difference. So I just circle out the difference. It's easier. So basically 1 difference, 2 difference, 3, and 4. So you actually have 4 differences over how many attributes or how many questions you ask, right? Sort of 1, 2, 3, 4, 5, 6, 7, 8, right? So again, this is actually my way. I think it's much easier. If you want to remember the formula, which I don't think is intuitive, is that you need to, essentially this actually says object I, so basically it's a cross tabulation of all the possible value combinations of any attributes, any binary attributes between object I and object J. So this, look at B. Let's look at B. B actually means how many cases, B is a number, okay? How many cases where object I take the value of 1 and object J take the value of 0. So if you want to work on this example, B should be, so I is 1 and B is 0. This is 1, 2, this is 2. Okay? But it doesn't matter. So you can see that B plus C is actually this one. B plus C is actually 1, 0 versus 0, 1. So essentially it's saying that how many cases they are different. The numerator is how many cases they are different. A plus B plus C plus D is actually how many attributes are there, how many features are there, right? So that's easy. You can just think, remember this kind of things. Now, the only change we need to do is to deal with the asymmetric version. So what's new? So for the asymmetric version, we actually need to deal with this D case carefully. So what does this D mean? D actually means object J takes object I takes 0 value, and both of them actually take 0 value. So in this case, how many cases we have? We have 1, 2, 3, right? We have 3 cases where both of them actually take 0. So by asymmetric, by convention, we put the most dominant value, which is the most likely value or default value, as 0. Okay? So the rationale of discounting this kind of case is that simply because, for example, you can't say 2 people are the same simply because let's say they don't eat pepper and they don't eat cake and they don't do something, right? Sort of, if let's say if you list all the activities, like in Olympics or whatever, right? There could be hundreds of them, and normal people, I'm talking about normal people, probably only do a handful of them. Let's say less than, let's say 8 or whatever activities. So basically, you can find plenty of sports, right? There are all sorts of sports that none of the people here actually do. So just based on the response from this kind of negative response does not really define any similarity. So that's the whole idea, okay? So what they do is that they actually need to discount the cases of D. D is, both of them are 0, so basically, in this case, it's actually 4/5. Okay, so for asymmetry case, you can see that it's actually A plus numerator the same, denominator actually don't have D. And this is actually called a Jaccard coefficient. So it got to have something to do with the Jaccard similarity we just talked about for sets, right? So what's the connection? The connection will actually tell you that, give you another perspective to understand why we do something like this. Okay, so just imagine that this is actually hat, this is a smile. I just, okay, it's too hard, but you get the idea. So for all the different dimensions, should not be different dimensions. I just call them A, B, C, D, E, F, G, H, because each one is a binary thing, right? So you can think about A is smiling or not, and B is wearing a hat or not, and so on and so forth. So we actually represent object I, which is a cartoon figure, using a binary vector. But equivalently, we can convert this into a set. We talk about bitmap index, right? We are actually using the same thing. In that case, we have the set, or essentially a list, and convert them into bitmap. Now we actually can do the inverse conversion. This will actually give us, say, okay, the object I is nothing but a set of B, right? This is B, this is D, and G, right? And the J, by the same token, it's going to be E, G, and H. So if you really draw the whole thing, the only common guy is actually G, right? G here. This is B and D. This is E and H. So the Jaccard will actually become the intersection, which is 1/5. So Jaccard is a similarity. Here we want a distance. So 1 minus J give you 4/5, right? So anyway, you can. So that's another way to, if you like, understand the formula, right? There are some example there. You can double check your understanding again this example. Just ignore this gender because gender is symmetric. I won't talk too much about this one. You probably can read through it. There are cases where you have we actually call it nominal variables. Sometimes we call it categorical ones. So these are actually a set of discrete states or values that you can't order them. Okay. For example, color. For example, profession. Whether you are lecturer, driver, clerk, whatever, right? So basically, each of them is a different value, and there is no way you can put them sorted in any order, right? You can't say yellow is in whatever sense better than red, which is better than green. Okay, even if you put into a color model, it's not going to give you a linearized order of all the colors. So what you do is that again, essentially these two methods will give you the same thing. Essentially, again, if you think about the object I, let's say this is red. Let's say it's car, right? You can think about the head part is red and the body part is blue. Let's say the rear part is whatever color, black. And another car is whatever 3 colors, right? So basically, both of them actually will give you the same thing. I'll probably talk about one-hot encoding first. One-hot encoding is easier. So one-hot encoding essentially says, okay, this is the, let's say, front color. I call it F color. So just assume that we only have these 4 values, okay, just to make it simple. So instead of putting red here, we can actually replace this value using a bitmap, right? So this is going to be, let's say red is the first one. It's going to be 1000. Let's say this is blue, then blue will actually be, so this is for I's F color, and J's F color is going to be 0010. And then you do the same thing for all the other things, okay? And then you actually can use the symmetric binary variable method, just we talk about here, trying to calculate its distance, okay? This will actually become the same as this one. This one is much simpler. You just look at, for example, here you have three features, and look at how many of them are actually identical. Or equivalently, you can think about how many of them are different. So basically, that will actually be, the difference will actually become the numerator, and the P is how many features are there. So in this case, 3 features, right? And another case is that you do have values, but to some extent, the actual value itself does not matter, okay? What matters is actually its rank. To some extent, I mean, if you think about web search results, right, you don't really care what's the internal score for the first results returned by, let's say, Google, right? All you care is that the order is the same, right? So then if you want to, let's say if you want to do whatever classification or clustering for the, let's say, top 10 results returned, in order to factor into consideration their position, relative position, right? I mean, for search engines, you can argue that you don't really have their internal scores. But even you do have their internal scores, you need to know that for a lot of reasons, I mean, the score, the absolute value of the score doesn't really mean too much. It's really the score really gives you some kind of ranking. And the rank order is actually more important. So what you do is that if you are ranked first to, let's say, the 10th, then this formula, you can just directly, I mean, use some example and you will see what's going on. So this will actually map everything into 0 to 1. Okay, so basically the first ranked objects will actually have a value converting to a numerical value of 0, and the second one, let's say there are 10, will be 0.1 and so on and so forth. Okay. Again, if you have 10, it's not really 0.1, it's 1/9 or something, because they need to make sure the 10th is actually 1. But basically, you get the idea. Okay, you only take the rank, and the rank is not bound. It's not really bounded. Like if you have several this kind of ordinal variables, you want to normalize it into the same range. So you normalize everything, the rank, into the range of 0 and 1. So that's the idea. And finally, there are some other variables which this usually happens for some kind of physical process. Okay, so one simple idea is that if you think about the level of earthquake, right? If we have level 5 and a level 6, I forgot what's the number. I think level 6 is 30 times more. 30 times as what's the word? Like violent or whatever, as the level 5. So it's not level 6 is slightly better than. I mean, it's like a fixed interval. It's actually the same ratio. Okay, the same thing goes when you do a shower and you want to tune the water temperature, right? So so I mean, within a small range, you don't feel the difference, but there, within a small range, if you change the knob, I mean, the water temperature will change quite a lot. So basically, there are a lot of physical scenarios where the data actually grows not linearly. And for whatever reason, a very common one is actually it grows exponentially. Okay, for those who actually know ordinary differential equation, I mean, for example, the spring, okay, this kind of vibration or whatever, it's essentially, if you do the solutions, it will all involve this kind of E. So this exponent function is actually kind of magic in many real scenarios. So in that case, you actually can take the log. Okay, actually, as we said, I mean, the level of the earthquake, let's say 5.3 level or whatever, right? It's actually already the logged value. Okay, so just in case you are given the original value, you can actually take the log. So another way to take the log is that if the value actually really goes through a very large range. So if you think another very simple example is the GDP, right? So if you look at the poor countries, it's going to be very, I don't know what's the number, maybe only let's say $200 per capita. For rich countries, maybe it's 20,000 or whatever, right? So if you plot everything, if you can imagine if you plot the GDP per capita on a plot, and the y-axis, if you don't take the log, then basically only a few countries is actually substantial there, and most of the because there are still a lot of poor countries, they will actually almost be close to the zero. You can't see any difference. And if you later you will see that if you just take the distance function, that's going to say, okay, all these countries are similar, right? So in that case, you can actually use log to reduce their differences. Okay, so finally, we actually talk about the clustering algorithms. We are going to mainly talk about three categories. These are representative ones, and for each, we actually talk about a few variants. Actually, except for even for spectral clustering, we do have slightly different variants. So the first one is actually partition-based method. So just assume that we actually all the data is again, this requires the data matrix as the input. Okay, of course there are ways to adapt it to other formats, but let's use two-dimensional example. So here you can see that if I ask you to partition to cluster all the points into, let's say let's say 3 clusters, I think most people will agree on. Except for some boundary conditions, you actually will agree. But the problem is that if I ask you to partition into 4 clusters or even 2 clusters, right? You don't really have. I don't think we'll reach a consensus, right? So the key point is that we want to, because you want a computer to do that, you need to set up objective criteria so that they can actually try their best to trying to find a good solution. So what are the criteria? So essentially what we do is that we say that the model goes like this. Okay, let's say if this is actually one cluster, C1. So what you can do is to select some kind of representatives. Again, I use S because I won't talk about some of the variations, but there are variations where they say, okay, why you only have one representative, right? You can have more than one, just like in some kind of election systems, the number of representatives is sort of proportional to your population, right? Let's say in the States. But let's say the simplest version is that you actually select one representative. And what's the definition of representative is still up for negotiation. Okay, so different algorithms will have different things, ways to do that. But when we talk about the k-means, there are actually a principal way to set the representative. So the role of the representative is to represent everybody in this cluster, right? Now, let's say this is C2, let's say this is C3, and you have a representative here, for whatever, I just randomly draw something, right? Now, what we can do is to say, okay, how good these representatives represent this kind of clustering. Because remember, we want points within the same cluster to be similar to each other, right? And by the same token, because we say, okay, every point is represented by a single point, let's say, then we really want everybody to be similar to the representative, at least in an average sense. We do allow people to have strong disagreement with one of the representatives, but on average, like the satisfaction rate should be high. So what you do is that if all the points belong to C1 is actually, I call it x1 up to xn. In C2, I call it y1 to yn. Actually, we don't need them. So let's say there are n points within C1. We can actually say, you actually can use x1 minus, let's say this is the representative R1. R1, you take the 2 norm. Again, you can use other norms, which you will see in your project. But basically, by default, we usually take 2 norm, which is the length. Okay? And you sum them up for all the i's from 1 to n, right? So this is actually you can take the square root as well. I mean, it doesn't matter too much, but basically, we use this one as some kind of criterion to say how good this R1 represents everything in C1, right? So you do expect that if this guy goes to very close to 0, then the situation must be this is R1, and all the points are just around it. That's the only case where you can, because each and every thing here, actually this is 2 norm to the power of 2. Okay, so basically this is actually always greater or equal to 0. So the only way it's going to be smaller to 0 is that everybody is actually well represented by R1, right? Okay, so this is actually our cost function. We haven't talked about the machine learning, but basically the cost is actually how bad cost is. You want to minimize the cost. So cost is how bad your solution is, your clustering is, and you want to minimize the cost. Okay, so again, I use center, but essentially it's the representative. That's the same thing. And here we use L2 distance. Okay, and we take the to the square, so you don't need to deal with the ugly square root, whatever. So now the question is that we have 2 things. One is that we don't even know which point are in which cluster. So I use xj belong to ci.